We're very pleased to have John Panitz with us today. John is a friend of many years who helped me over the years get started in my own research, for which I'm very grateful. John was a graduate student of Erwin Mueller, who was the father of atomic imaging. For those of you who have heard his name, Erwin Mueller is now dead, of course, but who first imaged atoms in the 1956. We keep seeing those claims come back time and time again. For the first time, atoms are imaged. I guess I don't know how many times I've seen things like that. In fact, to be accurate historically, Erwin Mueller did that first in the mid-50s, 56. And he first showed images of atoms. All high school students could then tell their teachers they really are round and bright, and electron clouds are more or less spheres. In any case, John did his dissertation with Professor Mueller at Penn State and developed the first atom probe. That is, the first time-of-flight mass spectrometer capable of single particle, single atom, single ion resolution. He then, on his own, went to Sandia Laboratories and developed a version of it known as the imaging atom probe. John, I'm sure, will talk a little bit about the imaging atom probe, so I won't steal his thunder. I was interested in the same subject about the same time, and John was very helpful in letting me in on much of his technology. We have been doing research together over the years, and in fact just returned at 2:30 in the morning from Baltimore, the American Vacuum Society meeting where we had presented a paper together. It's with great pleasure that I present John Panitz.
Thank you, John. The ability to see surfaces in atomic detail has really prompted continual advances in microscopy. But modern microscopes do a lot more than just image a surface. They tend to use analytic capabilities to analyze the surface composition or the bulk composition as well. And what I'd like to do today is tell you a little bit about a unique class of analytical instruments that are based on the field ion microscope. As John mentioned, a very powerful microscope developed many years ago by Erwin Mueller. These microscopes are absolutely unique. For those of you who have operated microscopes of any kind, you know that there are fundamental problems with just using them on a day-to-day basis. There's vibration, there's drift, you certainly have to turn a knob to focus, you worry about contrast, you worry about stigmation with electron microscopes. None of those problems exist with the field ion microscope. And what I'd like to do today is show you how that kind of microscope operates and how we've been able to use some analytic techniques to use and extend that microscope's capabilities both in material science and, we hope, in the realm of biological applications as well. To give you an idea of how this class of microscope works, since it's very unique, let me press this button and try to get the first slide. Does that work? Okay. I'm sorry, I'm trying to go back to the first slide. Thank you. Okay. I'd like you to imagine, for those of you who sort of remember your elementary physics courses, that we have an isolated metal sphere in space, a sphere whose radius is r. Now, if we create on the surface of that sphere charged particles by some means, we know that if we apply a potential to that sphere, there will be electric field distributed in space around it, and those charged particles will diverge from the sphere if they're allowed to do so. And we know that if we intercept at some distance from the sphere those particles with a detector, we'll get magnification. Those charged particles will follow electrostatic field lines that diverge radially into space. And so the magnification that you would get with such a device would simply depend upon how far you are away from the surface of the sphere. Now, there are many ways that you can create charged particles. You could do that with a laser by ionizing something that's on the surface of that sphere. You could create a very high negative potential on the surface of the sphere and therefore an electrostatic field that would pull electrons out of the surface by tunneling. That would be a field electron emission microscope. But another way is to create positive ions. And the way to create positive ions is to generate a very high field strength. In fact, in 1928, Oppenheimer, using the then newly developed quantum mechanics, predicted that if one created an electric field by some means that would have a magnitude of about 50 million volts per centimeter, the lifetime of a hydrogen atom molecule in space would be of the order of 1/10 of a second or so. Okay? But if you increase that field strength up to about 250 million volts per centimeter, right, 2.5 volts per angstrom, the lifetime of that hydrogen molecule would be very, very short indeed. And that meant that if you could create a very high field strength in some way, ionize these particular species, do that near the surface of a sphere, and allow those ions to travel into space, one could get an image formed by those positive ions. Now, of course, it's a very difficult problem in practice to create very high electric fields. You might imagine, for example, if I had two metal plates that I was placing 1 centimeter apart, and I tried to create an electric field of the order of 1/4 of a volt per angstrom or 250 million volts per centimeter, what I would have to do is separate these plates by 1 centimeter and apply 1/4 of a million volts between them. And of course they would arc over or they would break down. The way to avoid that problem is to use these very sharply curved surfaces, because the electric field depends on the radius of curvature of the surface itself and not how close the other electrode is. But how do you create very sharply pointed surfaces? One way to do it is to create them by etching a fine wire to a point. And one can, in an optical microscope, look at a picture of what these wires look like, and you see that they actually shape themselves to a very sharp point whose radius of curvature at the apex disappears. Can't see it at the resolution of this microscope. But in fact, if one put these specimens into the goniometer stage of electron microscope and looked in transmission, right, one would then see a highly magnified image, right, of the end of this wire, which is opaque. And as you see, you can create these wires that have radii of curvature of about 500 to 1,000 angstroms or so. So it's possible to create essentially spheres in space, not isolated, but nevertheless spherical contours that are very, very sharp. Now suppose we asked ourselves, what actually does the apex of this metal surface look like if we could look at it with atomic glasses? Well, we could build a little model of the crystal lattice that we formed this wire out of, and if we looked at the apex along the axis, we would see a surface that on an atomic scale was not smooth. After all, we have a hemisphere, hemispherical contour. We start out with a very large wire. It has to wind up at a point somewhere, and on an atomic scale, the way we do that is we have a plane of atoms of some kind. We have an edge, and then we go down one step. It's flat. We go down again, and gradually we build up a spherical contour that gets larger and larger. Now, if we wanted to create a very high electric field at the surface of this specimen by applying a high positive potential to it, we could ask ourselves, where on the surface of this metal specimen that we've modeled this way would the electric field be the highest? Well, obviously, it's going to be the highest where the radius of curvature is the greatest, and that's at these little one-atom steps, these little edges that occur. So we could take our model and we could highlight those areas by painting them with fluorescent paint and photograph our model in the dark. And if we did that, this is what we'd see. We've now highlighted only the edge atoms that are available where the electric field is the highest. And that is a simulation of a field ion microscope pattern. Now, the reason the field ion microscope is so powerful is because the only kind of image simulation that you need is essentially something as simple as this. But to give you a feeling for what a field ion microscope image actually looks like in real time and how well it reproduces this model, I have a videotape which was taken during real time imaging one of these surfaces. The surfaces is a BCC metal, tungsten, and we've imaged it in the field ion microscope by putting helium gas into the microscope and applying a high voltage and just seeing what happens. Now remember, helium has the highest ionization potential of all the gases. The electric field required to ionize helium is of the order of 4.5 volts per angstrom, 450 million volts per centimeter. All right? That's the field strength at which we'll see the first images. But we see some other things as well, which are kind of curious. Can I have that first tape, please? Now, in this first segment of the videotape that we're going to show, you'll see the screen of a field ion microscope as we gradually raise the voltage to display this process of field ionization, creating ions in a high electric field. Now, as the voltage is raised, you'll see some image spots that gradually appear and disappear. These are atoms on the surface that are essentially unstable in the field. But as the field is raised in real time to 450 million volts per centimeter, we get a characteristic field ion microscope image, looking very much like the model that you saw, in which the individual atoms on these edges or terraces are shown. Thank you for the tape. Can I have the slides back, please? To remind you again about magnification, remember, we have a highly curved surface of this wire, and we allow our ions to travel radially to a detector. Now, we might ask ourselves, what constitutes resolution in this microscope? How can we see atomic detail? Well, the way we see atomic detail in this microscope is by cooling the surface of the specimen and thereby cooling the helium gas that collides with the surface before it's ionized. Because if you think about it, a helium ion that's formed in space above one of these edges, right, will have some thermal velocity component parallel to the surface. And that velocity component will be preserved as the ion flies off to the screen. So if we have many ions created over the same region of the surface in time, we'll form a little area on the screen of contrast, a little disk of confusion that will get smaller as the transverse velocity component of the ion gets smaller. So we simply get better resolution by cooling the surface of the specimen and thereby cooling the gas. Right? We don't have diffraction effects to worry about because the mass of the ions are much greater than the mass of an electron. So unlike electron microscopes, the usual problems that constrain resolution are not available to us to worry about in an ion microscope. In fact, the resolution of this kind of microscope, delta, is simply the region, the extent of the area on the surface that has the high field associated with it, plus some factor that depends on the temperature of the specimen and the voltage that we apply. Now remember, the electric field depends on the voltage divided by the radius of this specimen at its apex. That means the resolution depends on the square root of the temperature divided by the electric field strength times some factor C and the radius of the tip itself. If we make the field high enough, that's automatic, 4.5 volts per angstrom. If we make the temperature low enough, say 80 degrees Kelvin, if we make the tip radius small enough, say 500 angstroms, that's easy to do, delta turns out to be about 2 angstroms. And when we do that, we get the field ion microscope pattern that most of you are used to seeing. This is a 110-oriented BCC metal lattice, tungsten, seen in atomic resolution. Remember what you see. All of these atoms that are resolved are the protruding atoms on the surface of that tip where the electric field is the highest. There are atoms present even in the dark areas. You just don't see them because the image contrast is such that most of the ionization takes place where the field is the highest. So we now have a picture. In fact, in this case, it's a color picture that's a superposition of 2 micrographs. When this picture was taken in the late 1960s, people didn't have computers and image processing systems to overlap images, so one projected these, used a beam splitter to combine them together through 2 colored filters, and was able to create an image that shows the difference between 2 events. 2 pictures were taken, one before and after bombarding a surface with helium ions, in this case, alpha particles. The red image taken before, a green image taken after, and where they superimpose, they look yellow. Those are unchanged positions of atoms. So one can now go into the field ion micrograph pattern and count changes on an atomic scale corresponding to some physical effect, some physical process that one uses in order to distort or change the lattice. So you can immediately see the power of this technique. If one, for example, was interested in radiation damage to a metal lattice, right, one can chart the course of that radiation damage as a function of flux by looking at pictures of the image before and after the event had taken place. A very powerful use of the color superposition technique involves charting the courses of single atoms deposited on a surface as they are perturbed by the interatomic forces of the lattice itself. Work done by Xian Song, Gert Ehrlich, Gary Kellogg, Bassett, a number of people throughout the world. This is a field ion microscope pattern. The red images correspond to atoms that were placed on the surface of a field ion microscope tip by thermal evaporation from a filament before the tip was heated. Remember, these images are taken at 20 degrees Kelvin. The experiment then is to raise the temperature to 300 degrees Kelvin, allow the atoms to form a random walk on the surface, and photograph them again in their new positions. And from the mean square displacement, one gets an activation energy for surface self-diffusion on the surface, but now one can chart the course of the atoms on an atomic scale. So the green atoms are after the fact, the red atoms are before, and the main lattice looks yellow because nothing has changed as far as the atom positions are concerned. People have used the field ion microscope to look at overlayer formation. This is silicon. This is a little silicon lattice that's been formed by thermal evaporation of silicon onto a tungsten surface at Penn State by Xian Song. This is a reconstructed tungsten 110 surface. It's a C2x2 root 45, root 45 reconstruction in which the individual atom positions are now resolved and can be measured, spacing roughly 2 angstroms center to center between the atoms. So field ion microscope, up to about 1965 or 68, was a very powerful way of looking at surfaces in atomic resolution. Remember, as you saw, no vibration, no focusing, no stigmation. You simply turn up the voltage and you see an image in atomic resolution of the surface. The problem, of course, comes when you try to do something more than just look at differences between two pictures. For example, you might say, well, yes, that sort of looks like a reconstruction because there's a geometric order. But what is that atom? What is that? Is that also part of the tungsten surface? Maybe it's an impurity that happens to be on the surface. Or, how do I know that these are actually silicon atoms on the surface? I've evaporated them from a tungsten filament, but how can I be sure? Well, that particular question plagued field ion microscopists for a very, very long time. And the solution to that question is the title of my talk, the atom probe microscopies, and in particular, the imaging atom probe that I'd like to talk about now. But to give you an appreciation for how that microscopy and analytic capability works, you have to understand one other physical effect that's important in field ion microscopy. We talked about field ionization, remember, the ability to ionize a gas atom in space close to the surface and therefore produce an image of the surface in atomic resolution. The other physical effect that we want to talk about is called field evaporation. Now, all of you are familiar with thermal evaporation. If we take a metal surface, for example, and we heat it to high temperatures, for example, by passing a current through it, we know it'll glow to incandescence, and metal atoms will be boiled off the surface. In fact, we know if we look at the mass to charge ratio of those species that come off the surface, that they're predominantly singly charged, but a lot of neutral atoms come off as well. The question is, could we, in fact, evaporate a surface at very low temperatures, at cryogenic temperatures, the conditions that the field ion microscope operates in? And the answer to that question is yes, and the physical phenomena that describes that process was discovered in Erwin Mueller's laboratory in 1956 when these first images were produced. That process is called field evaporation. Like thermal evaporation, but a high field at low temperature causing the effect. To give you an idea of sort of physically of how that works, imagine that you have a surface with metal atoms sitting on the surface. We apply a high positive bias to the surface. We create a high electric field. Now, as that field is increased, the electron clouds that surround those surface atoms get progressively depressed further and further into the surface, so that at high enough electric field strengths, and that's arbitrary, we just have to turn the voltage up, remember, no breakdown to worry about, we wind up with effectively an ion core sitting on a surface that's at a positive potential. And what we do is create an electrostatic force directed outwards that breaks the chemical bonding between that atom and the surface, and it evaporates. It flies off into space. But of course, unlike thermal evaporation, it doesn't just sort of go randomly into space. It follows the electric field lines, those radial electric field lines. And that's an actual important asset. Now, I'm going to show you that effect in real time by showing you another piece of a videotape. What I want you to keep in mind when I do this is that we are looking at an image with helium gas present, so we see the surface structure in atomic resolution. We're now going to raise the field, and we're going to cause the lattice to field evaporate. Now, what would you expect to happen? Okay. Obviously, the electric field is not uniform everywhere on the surface. It's highest at those edge atoms. So when the evaporation field was reached for whatever metal substrate we're interested in, those edge metal atoms would evaporate first, because that's where the field is the highest. Right? And they'd go away. And then you'd see the edge atoms of the plane a little bit further in. They'd be imaged. And then those would evaporate. And then you'd see the plane a little bit further in again, and then those would evaporate. Until finally, the entire crystal plane, the first one that you see, would completely disappear. So you'll see a series of shrinking circles corresponding to the edge atoms that were imaged, right, disappearing gradually as a function of time. Can I have the next part of the videotape? In this section of the videotape, then, let's hope this is the right section of the videotape. Nope, I'm sorry. Can we go back to the beginning of that tape? We want the second section of it.
Okay, what is the name of that section?
Should be called Field Evaporation.
All right, I'll be with you in 1 moment.
Thank you. Okay. In the meantime, let me describe how that effect occurs physically. Can I have the slides? Yeah, thank you. Okay, the way in which that effect then occurs is if we looked at that lattice from the side in cross-section, we would see these individual atom rows. The electric field would be the highest at these edge atoms, or any protruding atom that appeared on the surface, and we would, by applying an electric field, lower the potential energy barrier and then thermally activate, by normal thermally activation processes, an atom over that surface. So what you will see in the videotape section is these edge atoms disappearing, then the next atoms being imaged, and then those disappearing, and finally one atom or so left in the plane, and then that disappearing. Do we have that section of the tape? I think we're probably about ready to see it. This is all a marvel to me, to see all this electronic equipment here and trying to get used to it. Really quite intimidating to a speaker for the first time. Do we have that tape? Now, if you think about it, the importance of this process, and here it is. This is that field ion image, remember. We're raising the field now, and watch what happens to these edge atoms. The image gets a little blurrier, but you see what's happening? One plane has disappeared. Right? We raise the field, and another plane will disappear. Now, this is controllable. Right? We can stop the process, advance the process by just subtle changes in the applied voltage. Now, ask yourself, in the case of a BCC metal lattice, this particular plane is the 110 orientation. Thank you for the tape. If you think about that, every time one of those rings has collapsed, we've gone one atomic layer into the surface. 2.2 angstroms, built-in depth marker. Okay? So what we can do now is not only look at the surface, but we can look at what's inside the surface by field evaporating, by eroding the surface away and exposing something of interest. Now, there's been a great number of metallurgical applications using this process. Can I have the slides back again? And in fact, one of the nicest examples, I hope you can see it here, it's a little bit dark, are some images, field ion images of a precipitate taken during a successive series of field evaporation stages. This is a copper iron precipitate which appears as a contrast variation in the field ion microscope image. A depth scale is written on the top of the photographs. These were done by Sid Brenner when he was at U.S. Steel. So what we're doing now is we're tomographically slicing through this precipitate by field evaporation. Notice, when we go down into the lattice by roughly 2 angstroms, 2.4 angstroms, we see more of the precipitate. We go a little bit further, the precipitate develops more completely. Now the precipitate starts getting smaller and smaller again, right, because we've gone through it. So we have a way of imaging in atomic resolution as a function of depth, not only as a function of spatial variation. But of course, the same problem appears. We can field evaporate, we can go through something, but how do you know that's a copper iron precipitate? I mean, I'm telling you that, and you've got to believe me, right? But actually, we can do that with the atom probe techniques. The atom probe is sort of a simple device. Remember what we're doing. We're removing material from the surface. So why lose it? Why not just stick it into a mass spectrometer? Right? And in fact, why not make a time-of-flight mass spectrometer? Right? And time-of-flight mass spectrometers are kind of simple to do. See, the procedure is very easy. We put a DC voltage onto the specimen and we create a field ion microscope image. Right? But we're clever. We put a little hole in the field ion microscope screen. And then we provide a facility for moving this tip in X and Y so that we can shift this image, right, over the hole until something in the image, like that precipitate particle we were interested in, till its image falls over the hole. Okay? Then what do? We apply a high voltage pulse on top of the DC bias. And that high voltage pulse is enough in amplitude, right, to field evaporate the surface. And now all of those ions fly off the surface, strike the screen, except the one we were interested in, right, that formed the images of those particles, and those go through the hole to the detector. Pretty clever, right? In fact, it's pretty easy. It's elegantly easy. Because what do you need to do time-of-flight mass spectroscopy? You need a way of applying voltage to the specimen surface, and you need a distance over which the ion drifts, a field-free distance. And then the most mathematics that you need, right, is to know that the kinetic energy of the ion, 1/2 mv squared, is just its charge times the voltage you apply, the sum of the pulse plus the DC voltage. And velocity times time equals distance after the ion flies away from the surface. And that in turn tells you that the mass-to-charge ratio is some constant that depends upon the distance the ion travels, which you can measure, the voltage, which you can measure, and the travel time, which you can measure, because you used a high-voltage pulse, and the start of that pulse can trigger an oscilloscope sweep. When the ions arrive at the detector, they're displayed on the oscilloscope sweep, and you measure their travel time directly. Do a lot of clever things. You can adjust your distances, for example, so that this becomes the year in which you did the experiment. There are all kinds of variations of time-of-flight mass spectroscopy that are possible. Okay, with that kind of technique then, and the power of depth profiling, you can do a lot of neat things. For example, one problem that we looked at rather extensively were what happens in an operating tokamak reactor, an operating fusion reactor, to plasma species that escape from magnetic confinement and strike the wall. Turns out to be a severe materials problem. And here's an example in which we have a field ion microscope pattern damaged surface as a result of being exposed to plasma species. And as we field evaporate successively and take mass spectra at the same time, we determine compositional changes as a function of depth. So we can look at the implantation of helium or hydrogen in an operating fusion reactor in atomic resolution as a function of depth. And one of the things that we proposed to do originally was to extract from the depth distribution an energy distribution. Should be fairly straightforward. And it is, except that these experiments are done at room temperature, and as most of you know, hydrogen diffuses in metals rather rapidly. The idea to do this is with silicon and damage trap the hydrogen, and Tom Pickrow and a group at Sandia actually were able to do that using other less step-sensitive techniques. The problem with field ion microscopy, up until very recently, is that one always had to use metals, conductors of some kind. Now, before I sort of show you the variations that allow us to look at semiconductors and glasses, I want you to think about this. Remember, I was showing you images of field evaporation in which we had a field ion microscope pattern there that sort of showed you what was going on. Imagine we pump the gas out. After all of these ion species are being removed from the surface atomic layer at a time. They're striking a detector. We should be able to image them directly, right, without a gas. That requires a detector with single ion detection sensitivity and some spatial ability to resolve the impact of the individual ions. Those detectors became available in the early 1970s. They're called channel plate electron multiplier arrays. They detect single ion impacts, produce an intense electron image that gets focused onto a fluorescent screen. So as far as you're concerned, you see an image during normal conditions of single ion impacts. The process of removing things from the surface is called field desorption, another word. It's like field evaporation. It's exactly the same process, but now we're self-imaging the surface. Can I have that third section of the videotape, the one that says field desorption? What I'd like to show you is what actually happens as we raise the voltage now, and what you'll see is what you see as we DC field evaporate. We just raised the voltage, same conditions we had before when gas was present. We have some background noise. That's random background events because we have single ion detection sensitivity. But as we reach the critical field for field evaporation, the image spot density will increase, and finally you'll see those planes field evaporating. Single ions being self-imaged by a process of field desorption. Okay? Now, what do you got? Thank you for the tape. What do you got? You got a technique that has time-of-flight mass spectroscopy, can look at a surface by self-imaging the atoms that come off as you go further and further into the interior. But the ions that come off arrive sequentially in time at the detector, right? And what we did was to integrate over the arrival of all those ions. Suppose we turn the detector on coincidentally with the arrival of one mass-to-charge species that we're interested in, and turn it off after that one has arrived. Then only that mass-to-charge species will be imaged. We can take a picture of it, and we can have a two-dimensional map in atomic resolution of anything we're interested in. Oxygen, hydrogen, carbon. Remember, it's a mass spectrometer. It's sensitive to all elements. Uranium. We can image the precipitate particles if we want to. Self-image them, right, in the particular mass-to-charge that we're interested in doing. That device is called the imaging atom probe. Can I have the next slide, please? Now, to appreciate instrumentation, and I won't show you any pictures of instruments, but I'll show you a schematic. Remember, the way we do this experiment effectively is we apply a high voltage pulse from this desorption pulsar. We allow it to travel down to the tip. We capacitively couple it. The specimen is called a tip. We capacitively couple it so that we can put a DC bias on top of it as well. And we use that pulse to trigger an oscilloscope sweep so we can determine a mass-to-charge ratio. But we can also use that pulse to trigger another pulse generator that supplies a pulse to turn on the detectors, coincidentally with the arrival of a particular mass-to-charge ratio. And that's all that's needed. Very simple instrumentation. We have very good mass resolution. Remember now, we have to be sort of close because we want to get the image diverges radially into space, right? So if we're too far away, we need a big detector. So experimental constraints say be about 10 or 11 centimeters away, use about a 3-inch detector. We're talking about travel times of the order of 10, 20, 30, 40 nanoseconds, depending on the voltage for hydrogen. And here's rhodium hydride, part of an examination of rhodium hydride, just to show you that with a very simple mass spectrometer, time-of-flight mass spectrometer, you have single AMU mass resolution at the low end of the scale. The reason it works so well is that all the species come from the same point in space. there is no uncertainty about what the distance is. And since they all field desorb more or less at the same time, they all accelerate to the same voltage, so they all have the same kinetic energy. That's why the mass resolution is so good. Now it turns out up at higher masses it gets progressively worse, but if one is willing to play experimentally, one can get better than single mass resolution at mass 60. We're limited with the imaging atom probe in its simplest form to about single mass resolution up to m/n equals 60. So it's very hard to do isotopes up at that range, but you can still resolve something about them. That's mass resolution. What about pictures? Well, here's a sequence that shows you a transmission electron microscope image, fascinating pen, of a tip with two grain boundaries. See them? Okay. This is a corresponding field ion microscope image in which one of the grain boundaries we see as a dark line. Remember, if we etch through two single crystallites in our wire, we see a grain boundary in the image. In fact, you know, field ion microscopy was the first technique that showed that grain boundaries don't extend into the lattice by many, many, many angstroms. There's a very abrupt step. There's an image of a grain boundary, and here's an image time-gated for deuterium, because what we were interested in doing in this case is looking at the diffusion of deuterium damage trapped at grain boundaries in crystal lattices, something that metallurgists are beginning to use now quite extensively. This particular technique is a nice complement to the electron microscope because it extends its capability, analytic capability, beyond the range that electron microscopes nominally work at now. Suppose you were interested in hydrogen. Here's hydrogen that segregates to carbon impurities within an iridium lattice. We were interested in what happens if we could actually look at the number density of hydrogen and how its segregation properties are affected by the way in which the alloys are prepared. Turns out this particular one had a certain impurity level of carbon. Remember, time-gated for H+, so we know what each of those spots represents, right? Individual hydrogen atoms. And finally, a kind of very new example. This is some work that John Wren and I just completed. We were very interested in the question of using this process of field desorption and time gating for a species to ask the question, could we possibly look at large area surfaces? Everything I've told you about works well, smoothly, reproducibly, no problem, but you need a sharp tip. Question is that a problem? Well, in some cases it is. Now, obviously, in cases in which you're interested in looking at a precipitate particle within a lattice, and that precipitate particle is much smaller than the radius of the tip, you don't care. It's there, and it's not constrained in some way by this volume of material that you have to work with. But suppose you were looking at something else, something that was much larger. Now, obviously, you can use this technique to look at surface processes, catalytic processes like hydrogen diffusion, as we looked at. Suppose you were looking at reconstruction. I showed you an example in the field ion microscope, but there are other reconstructions that people have become very interested in, reconstructions of semiconductors. Most of you have probably heard about the 7x7 reconstruction of silicon that has been seen by a new microscope called the scanning tunneling microscope. Field ion microscopy has never seen real, true reconstructions of that kind. And the reason is that the crystal planes are very small. That means that if the unit cell of the reconstructed lattice is comparable to the size of the crystal plane, then the edge atoms form a boundary condition that pins the lattice in a unique configuration and doesn't allow the reconstruction to occur. Or if it's too small, you just can't pack somehow the right crystal lattice into that size. So we'd like to go to much larger crystal planes, 4,000 angstroms across, 5,000 angstroms across, right? How do we do it? Well, you can't do it with field ion microscopy because the field isn't high enough there, right? It's sort of local and it ripples smoothly across the surface. The way that John and I developed is a process called CO field desorption, and it's kind of neat. What we do is we put carbon monoxide into the gas phase, and we allow it to condense onto the surface at 20 degrees Kelvin, and we choose the temperature so that we don't form a condensed multilayer. We only form one or two monolayers on the surface at that temperature. Okay? And then we pop it off with a high voltage pulse, and we image it. And you might say to yourself, well, that seems like an involved process. Why is that any advantage? You can do this all by field ionization. The advantage is the CO comes off at a low field strength of the order of 1 volt per angstrom. Now you might say, gee, that's not very low, right? I mean, that's still 100 million volts per centimeter. It's pretty high. But in the field ion game, it's very low, and that has obvious advantages, as I'll show you. For example, here's a field ion micrograph image of a tungsten surface. And we're going to take one of the higher index planes that normally in a field ion image shows contrast at the edge, as they all do, as we told you. But if I adsorb CO on the surface and pop it off, this is a CO plus image of the surface. I can see detail near the center of the plane, including vacancies, these dark areas, right, that are normally not observed. And the only way you could observe them was by raising the field evaporating the plane away slowly, and looking for their absence in the ion image. Much more effective way. This is a hydrogen image of the surface. Doesn't look very good at all because hydrogen, curiously enough, at 20 degrees Kelvin doesn't stick, so shouldn't form an image at all, but it does. And the reason it does is because it not only sticks chemically to the surface, but it forms a field-induced dipole-dipole bond. The first known example of an effect called field adsorption. The higher the field is, the stronger the stuff sticks to the surface. All right? So a field ion microscope image is not clean. That's the first thing that I'm telling you. There's always hydrogen around, and it's always there, but it's invisible in the field ion image. And in fact, helium binds to the surface as well. You can, of course, image wear by popping it off, but it'll only show you the high field regions where it binds. CO goes everywhere onto the surface, comes off at a much lower field strength, and images the surface entirely. If you then created a metal surface with large thermal facets, you would see in a field ion microscope image something that looked like this. Large dark areas. This crystal plane, the 110 plane, is about 3,000 angstroms across. You see no detail in the center of it. You only see detail where these thermal facets join together. Okay? That field ion image is because the radius of curvature is sharp. If we now apply CO and desorb it from the surface with a high voltage pulse, what you see is a CO plus image that looks sort of like the field ion microscope image. But now we can raise the field without changing the lattice because CO desorbs at a low enough field strength. We won't field evaporate. And that means we can see more of the CO from the center of the plane. And finally, if we go to a high enough field strength, we get CO from the whole surface, including the center of this plane, 3,000 angstroms across. Here's the small net plane edge. You see the edge atoms of it. So we're even able now to look at very large planes by field ion microscopy. And one of the next steps John and I have been threatening to try is to look at the silicon reconstruction by this technique, because it's certainly something that one can do, or at least in principle one can do. Okay, let me just conclude by giving you a couple of examples and then a 5-minute delve into the realm of biology. First of all, field ion microscopy, as you've seen it now, and analytical instrumentation, has been restricted to metals. What about glasses, and what about semiconductors? Well, it turns out both of those are possible to look at now. Metals, glasses, you can do it pretty easily. One way to do it is to coat the glass. This is a transmission electron microscope image of a glass specimen that's been partially coated with metal. That's what this irregular area is here. Okay? In fact, we evaporated metal uniformly over the whole tip, and then we field evaporated the metal away from the apex. I applied a high field, the metal popped off. Okay? But there's enough metal close enough to the apex, right, within a couple of hundred angstroms, that there's a little bit of charge transfer on the surface. And that means a high voltage pulse can be propagated, and we can field evaporate the glass itself. Okay? And when one does that, work done by Gary Kellogg at Sandia, in this case, one gets a mass spectra that has the predominant species characteristic of the Pyrex glass itself, as well as some other things. And then as one goes further and further through the surface of that metal layer, one sees only the species that are characteristic of the metal. I'm sorry, these two slides are reversed. This monitor is a little blurry. This one shows you what you should see first. When the metal coating is there, we're field evaporating it. You see the chromium peaks for the chromium metal coating that corresponds to species on this, of the metal coating itself. Once we've popped the coating away, then one sees the species that are characteristic of the glass layer itself. So you can even look at glasses, and by using laser pulses to thermally raise the temperature, remember this field evaporation is a thermally activated process. Go to high temperatures, no field, get evaporation. Go to low temperatures, high fields, get evaporation. Go somewhere in between, you can use temperature to evaporate. That means you don't have to propagate a high voltage pulse. Okay? And that in turn means that you can use silicon samples as well. That work is primarily being done by Tsien Song and Gary Kellogg. Tsien at Penn State, Gary Kellogg at Sandia National Laboratories, who pioneered that variation of the imaging atom probe called the pulsed laser atom probe. Finally, in the last 3 minutes or so, 4 minutes, I'd like to tell you what I've really been working on. What I've been telling you is what I've been working on up to about 4 or 5 years ago. But at that time, a new challenge appeared in field ion microscopy. And that challenge is to use all of this wonderful technology to look at organics and large organic molecules and coatings. Now you might say to yourself, well, why can't you look at them? The reason you can't look at them with field ion microscopy is because the field strengths are too high. In fact, if you raise the field high enough, that coating of atoms, of molecules on the surface, organic material, will field desorb, just like the metal will, but it'll occur at much lower field strengths. In fact, it has the ornery habit of field desorbing somewhere between 0.3 volt per angstrom and 0.7 volt per angstrom. That's well below field ion imaging fields. Remember, 4.5 volts per angstrom for helium, for hydrogen, which you can use, about 2.5 volts per angstrom. Too high a field. Now you see why we were interested in CO+. That comes off at about 1 volt per angstrom. It's almost there, but not quite. How can you do it? Well, what I'm going to show you now, right, will be the first images of proteins, large biological organic macromolecules on metal surfaces, taken with the first successful application of physisorption to anything that I can think of that's practically useful. Right? Physisorption is a technique where you condense stuff onto a surface and you sort of get it out of your vacuum system. Well, we're using that technique to image biological molecules. I'm going to give you the punchline first. The resolution is not like the resolution of a field ion microscope image. It's about 20 angstroms. So not too many people are interested yet. But the hope is to increase the resolution. And why is that of interest? It's of interest because we don't have to shadow or stain or selectively change the contour of a molecule to enhance its contrast, as you have to do in the electron microscope. The other advantage is we can look at metal surfaces on which these species are adsorbed. And if you're a member of the particular group who likes to talk about bioelectronics in the future, then one of the future bioelectronic systems involves molecules on silicon and metal surfaces. And those are very hard systems to look at in the transmission electron microscope at the resolution you want. That's why we're interested in doing this. How do we do it? Can I have the slide again? What we do is we take a biological molecule, in yellow here, and we put it on a field emitter tip. That's not very difficult. I'm not going to talk about that. If there are any questions, I'll answer them. It's really easy to do. Typically, we use concentrations of molecules in solution about 1 microgram per ml to 1/10 of a microgram per ml. We wait for a certain length of time. Molecules adsorb on all the surfaces. Remove the tip carefully from solution. Put it into our vacuum system. Cool it to 20 Kelvin and spray liquid onto the surface. And that liquid condenses into an amorphous ice layer. Now, if you choose the liquid carefully, we've used benzene, but this summer we found water works as well, which is wonderful if you do biology. What you find is this ice layer can be removed at very low field strengths, about 0.3 of a volt per angstrom. For benzene. What does that mean? That means the molecule doesn't go away, but we can remove the layer of ice. What does that do? Well, remember, we can self-image this ice layer by time gating, right, for whatever that species is, and then look at the image that's formed on a detector. And so what you'd expect to see as you raise the field strength is a dark region appearing as we begin exposing the contour of the molecule in the ice layer. Right? It's sort of like, imagine a rock in a mound of snow, and you're melting the snow. You're subliming it, right? And you're looking down at it from the top. And a little bit of the rock appears, and then a little bit more, and then a little bit more, and then a little bit more, right? Until you've exposed the rock completely. That's sublimation in a high field, field evaporation or field desorption, and that's how we get our images. In fact, as the process proceeds, one exposes more and more of the molecule. Can I have the final short section of tape, please? I'm going to show you it in real time. This is a rather unusual one because these are results that came this summer, in which we used water as the ice layer. And the real advantage of using water if you do biology is because you don't really have to take the molecule out of the water in the first place and put it in vacuum. You can freeze it in the water, transfer it cold into this microscope, remove the water as you apply the field, and get an image. So what we're doing now is we're raising the field strength by raising the voltage, ramping it linearly in this case, because we know in this case that all of the species that come off the surface are ones that correspond to those from the ice layer. What you'll see happen is as we peel away this layer, you'll see dark areas developing, and then we're going to integrate, like you would on a photographic film, and we get a series of contours. And those dark areas correspond to clusters of molecules sitting on the surface. It's very reproducible. Right? We're going to go up one more time just to show you that. We re-spray water on the surface, we re-evaporate onto the surface, and we produce the contours once again. Unstained, unshadowed biological molecules on a metal surface. But remember, in this information, we're throwing a lot away. See, the three-dimensional detail is appearing. That's two integrations. A lot of signal to noise, good contrast. Thank you for the tape. If we combine all those contours together, we can get a three-dimensional image. Can I have the next one? Here's a picture of some molecules called ferritin in the transmission electron microscope. Their iron-rich core is all you can see. You can't see their protein shell because it's not stained. On a field emitter tip, we're going to image over this area. And what you see is an image like this. This is a three-dimensional reconstruction, very simple, of ferritin clusters. This is a large one made up of individual ferritin molecules, but you can't resolve them because the resolution is only about 20 angstroms. on this picture. This is the size of one ferritin molecule. That's what it looks like. In fact, in higher resolution, higher magnification, you see things sort of wash out. These are 4 ferritin molecules, and if you look at them in the electron microscope at the same magnification on a different sample, you see the iron-rich core, and these molecules are separated by the invisible protein shell that surrounds them. Okay? Roughly the same size as the features we see. Just to show you that things don't always look like balls, here's an example of RecA-coated DNA. RecA is a DNA binding protein. These are filamentous strands of DNA coated with that protein at a resolution that's comparable but not quite as good as what you can get by staining and shadowing in the electron microscope. So that's what we do. That's the kind of pictures that we produce. And the hope ultimately now is to extend at least the biological and organic imaging to a whole new range of materials coated on metal surfaces. But regardless of that, the message that I want to leave with you today is that it is not a wonderful, new, and novel feature to see a surface in atomic resolution. In fact, I want you to realize that not only can you see a surface in atomic resolution, but you can see what's in the surface as a function of depth with an angstrom scale, and you can also see what's adsorbed on the surface or within the lattice. All species, hydrogen, CO, anything you were looking at particularly. The reason the technology hasn't really, everybody hasn't grabbed it right and run with it is because you have to form tips. Provided your problem is such that the thing you're looking at is small compared to the radius of the tip, you're okay. Obviously, if what you were looking at was much larger, you'd have difficulties. That's why biological molecules are a wonderful choice. Organic coatings are a wonderful choice because you don't care how big they are generally. And small precipitate particles that are just below the resolution of the electron microscope. One of the exciting things that's coming up that John and I are talking about now is to combine this imaging atom probe instrument with a conventional transmission electron microscope so that in the same instrument you can do all of these studies, right, without breaking the vacuum. Looks like a very challenging project, but something that we hope to do in the very near future. Thank you. Questions?
Down.
Questions? Either everything is completely lucid or everyone is asleep and lost. I'm not sure which.
Question from MCNC.
Pardon?
Question from MCNC.
You watch the screen back there, people off campus.
Oh, okay. Yes.
Okay. In your video tape, about field evaporation,
Yeah.
You showed the atoms going one after another. Is that the voltage is same? The voltage applied in the probe is same or is changing with time?
What we are doing in the particular tape I showed you is to apply a voltage, a constant voltage that's high enough to generate an electric field that will remove the surface atoms and watch what happens as a function of time. Now the process eventually stops. It doesn't go on forever. And the reason it stops is because as you field evaporate the surface, you remove material, the tip radius increases, and the field strength is the voltage, which is constant, divided by the radius. So as the radius goes up, the field strength goes down, and the process stops. And you have to up the voltage to continue it.
What is the time scale you are talking about? Like what is the time scale between one atom going out, the next going out? Do you have an idea of that?
Well, it really it happens for all practical purposes instantaneously.
Right.
If we measure the time of flight mass spectra, we do not see any suggestion of some process that occurs on a time scale as short as 1 nanosecond. if there is a discrimination between the desorption time of one atom and another, it's much shorter than 1 nanosecond.
Thank you.
He was asking if the tape was shot in real time.
Yeah, the other point that John is mentioning, that tape was shot in real time. Remember, we applied a constant fixed voltage and then just looked at what happened as a function of time. Yes?
When you apply the field, the positions of those atoms near the surface are not exactly of those in the bulk. So it means you're not really getting the accurate information on the positions as they will be, as if they're well inside. It means you're getting a field-affected positions of the atoms rather than the exact atoms.
That's right. I mean, it depends on... The question, of course, is what you're trying to get as far as information is concerned from a field ion microscope image. Now, the point that's being made is well taken. There is a high electric field present, and that high electric field has consequences. One consequence is it removes things from the surface. Another consequence is it causes things to adsorb on the surface. But a third consequence, as you were suggesting, is that a very high electrostatic field stress exists at the lattice, which means that the position of the surface atoms are not exactly what they are in the bulk. After all, at 4.5 volts per angstrom, the electrostatic field stress is of the order of 10 to the 9th dynes per square centimeter, about a half a ton per square millimeter. That distorts most things drastically. On the other hand, the kind of imaging that we're doing now with CO greatly reduces those field stresses. And if you look at how serious those effects are, they're noticeable, but they don't change the effective position of the atoms by 200 or 300%. I mean, the effective change is perhaps 10 or 20% at most. So if you're looking for accurate lattice information, position of atoms, you certainly have to be very careful if you extract that from field ion microscopy. But the point you're bringing up is, of course, you have to know your instrument. There's no instrument that doesn't interact in some way with the surface. The thing about field ion is people are always concerned about that problem because they use it in a variety of ways. If you take your electron beam and do low-energy electron diffraction of a surface, for example, and try to get from the lead patterns some information about surface structure, you know there are constraints also. Right? There's a coherence distance associated with the electron beam that means the resolution is washed out to the order of 20 angstroms. So you see periodic structures only. The great thing about field ion, even though that's a problem that you mentioned, is that you can see aperiodic structures. Right? But you're right, the point is well taken.
If there is an ion which is in a charged state, which is not in a neutral state, the influence is more so because on the charged ion the field effect is a lot more than.
Well, again, all of those problems depend upon the magnitude of the field that you apply. And a person who is prudent, right, images a surface, if you're interested in structural information, with a high field, helium imaging, then images it with hydrogen at a little worse resolution at 1/4 of that field strength, right? And then might image it with CO at even a lower field strength and looks for changes and sees how drastic those changes are. There are changes, but they're not drastic. The image doesn't change completely, for example. Yes?
You mentioned as an application the measurement of the grain boundary diffusivity of deuterium.
Yep.
I would argue that that's probably not the grain boundary diffusivity because you're measuring along the edge of the grain boundary intersecting the surface.
Yes, right.
The question, though, is that significantly different than the diffusivity of the deuterium just on a surface without being on the grain boundary?
No, we really don't think it is. Now, precise measurements of that particular parameter haven't been made. But if you look at the way the experimental conditions are done, normally these experiments are done implanting the deuterium at very low temperatures. Typically the tip temperatures are 20 degrees Kelvin and less. So what one does is one raises the temperature, for example, to cause diffusion, and then immediately quenches the temperature by allowing it to rapidly go down to low temperature and locks in whatever that distribution is. Now, John has spent a great deal of time looking at that particular problem, and it's not a trivial one, obviously. The way in which one would like to do the experiments now that lasers have become available, I think, is to raise the temperature of the surface instantaneously within a very short duration of time with a very high-powered laser. So that what one would do is sort of implant, raise the temperature, not enough to thermally desorb, but perhaps to room temperature. If you do that with a 4 nanosecond laser pulse, then you quench it immediately to 20 degrees. And so hopefully the distributions that you could get as a result of some process of rapid quenching with diffusion would be realistic. Most of what I've showed you are what are called preliminary experiments in the trade. There have been a great many of those, and one of the criticisms of field ion microscopy, and probably a very valid one, is that with the exception of some very long and tedious studies, but very beautiful and elegant ones, done by some very well-known people in the field, David Seidman for neutron damage, Gerd Ehrlich for single atom diffusion, Gary Kellogg, Xian Song. A lot of the experiments were sort of showing what you could do. Turns out that the diffusion problem is a serious one, but I think you can get around it. Yes?
Analytical question. You showed these images of, I believe it was precipitates of iron and copper, whatever was it that Brenner did. Now, if the precipitate were an intermetallic compound, could you get a reasonably close fix on the composition?
Yes. I don't have curves of that. There is one problem that you have to worry about in general. Remember, well, this is sort of like the problem you face with a sputtering technique that has different sputtering yields, okay? Only in our case, the problem is, suppose you have, for example, beryllium in a copper lattice, okay? Well, the beryllium has a lower ionization potential, and so if you field evaporate the copper, the beryllium comes off as an ion because the field is high enough. Roughly scales like the ionization potential, not quite. If you had the reverse, the beryllium lattice would dissolve, but the copper wouldn't ionize, so you wouldn't see it. It would just sort of disappear as a neutral. So you have to be very careful that the field strength is high enough, and that often means over-voltaging by a certain amount. But with that particular constraint in mind when you do the experiment, yes, you can do that problem. You can look at that problem.